We saw in the last video that the equilibrium equations, or the first derivative of the energy, can be written like this for our model simply supported column with 3 rigid links and 2 springs. Now let's do the second derivative. So first let's do d squared v by dw1 squared, and to do that let's just pull out the term dv by dw1 from the previous equation. So if we did d squared v by dw1 squared by the product rule, we can write it as the derivative of the first matrix times the second matrix plus the first matrix times the derivative of the second matrix. Now if we were to evaluate the second derivative at an equilibrium point, we know that that vector is 0 because those are the equilibrium equations from the free body diagram approach. So at an equilibrium point, the second derivative has a simpler formula, which is the first matrix. Now we can do the derivative of the second matrix and plug in things like d theta 1 by dw1 and so on, and we get that. Similarly, d squared v by dw2 dw1, evaluated at an equilibrium point, has this kind of a formula. Again, we've plugged in for things like d theta 1 by dw2 and so on. So the second derivative matrix, if we collect all of this, the second derivative matrix with these 4 components evaluated at an equilibrium point can be written as this first matrix times the derivative of the second matrix, and which has these following terms. Again, all of this is just direct calculation. There's nothing very deep or profound about this. And you should check that all these calculations make sense. So at this stage, unlike with the toy column where we wanted to explore post-buckling behavior, here we will be content with simply asking about the stability of the vertical equilibrium position. Or in other words, when does the vertical equilibrium position transition from being stable to unstable, or what is the buckling load? So for the vertical equilibrium position, W1 equals W2 equals 0, and H1 equals H2 equals H3 equals L. If we plug all this into the second derivative matrix, we get something that is even simpler. Because 1 over H1 plus 1 over H2, for example, becomes just 1 over L plus 1 over L, that's 2 over L. That's how this simplifies. Now for one degree of freedom systems, like the bead and the toy column, we said that the equilibrium point is stable if the second derivative is positive. For 2 degree of freedom system, you can imagine that the notion generalizes to positive definiteness of a matrix. And we've already seen what positive definiteness of a matrix means. So the 2 degree of freedom system is stable if the second derivative matrix is positive definite. Now, so if we look at that second derivative matrix, for small values of the load P, for example, if P is equal to 0, it's easy to see that that matrix is positive definite. So for small values of P, that matrix is positive definite. But as the load increases, there comes, and the matrix is positive definite, both of its eigenvalues are positive. Now, as we increase P, there comes a time when the matrix just stops being positive definite, or one of its eigenvalues just becomes 0. Which means there is a vector, which when multiplied by the matrix will give 0. So let's write that part. So there is a vector W1, W2, which if we multiply by the matrix gives 0, which means the matrix has 0 eigenvalue. So that matrix times, there is a vector W1, W2 in such a way that this is 0. Now, that pre-multiplying matrix is non-singular, which means this is the same condition as simply the second matrix times the vector is 0. Now, if we rearrange all of this, this amounts to saying find a P such that that matrix times W1, W2 is P over KL times W1, W2. And this P over KL we'll just call lambda. So this looks like AW equals lambda W, which is an eigenvalue problem. So we see that computing the buckling load of a column is actually an eigenvalue problem. The eigenvalues give the buckling load. It's very similar to, you've probably seen in your structural dynamics course by now, that computing natural frequencies of a multi-degree of freedom system is an eigenvalue problem as well. So this is a similar kind of problem. So in MATLAB, we can do this problem. We can solve this by doing W lambda equals eig of the matrix 2 minus 1 minus 1, 2. And if we do the eigenvalue problem, we get two values of lambda. Lambda equals 1 and lambda equals 3. For lambda equals 1, because P over KL is equal to lambda, so lambda equals 1 means P equals KL. The eigenvector is 1, 1, which represents a buckled mode as shown in that picture. And similarly, for lambda equals 3, P equals 3K over L. The eigenvector is 1 minus 1, and the buckled mode is that zigzag mode as shown there. And that's possible if there is some latent restraint in it.